Okay, so SN2 reactions. We're going to start with SN2 and then we'll go visit SN1. So, first things first, what does SN2 stand for? Because good news, it basically spells out what's happening, some of what's happening, okay? So, it stands for nucleophilic substitution. And, well, I guess I could say up here it's bimolecular. Bimolecular. Yes. All right, so it's bimolecular nucleophilic substitution. That's what it stands for. Now, nucleophilic substitution just means we're using a nucleophile to do the substitution. Okay, so, makes sense. What does the bimolecular mean, though? What does that mean? What does this 2 mean? Well, it means that the rate determining step all right, so rate determining step. I don't like writing this out, so from here on out, anytime I want to say rate determining step, I'm going to say RDS, okay? So the rate determining step is bimolecular. That's cool, but what does that mean? Well, it just means that in the slow step, because remember, a rate determining step is just the slowest step that occurs, there are 2 molecules involved. So there's 2 molecules involved in the rate determining step, okay? And we're going to go over that. Now, here's the interesting thing, and a lot of people memorize this, where SN2 reactions are 1-step reactions, okay? Whereas SN1 reactions are 2-step reactions, all right? Okay, so think about it this way. If SN2 is a 1-step reaction, that means it's all 1 step, which means that that 1 step must also be classified as the slowest step because it's the only step that's happening, okay? So this step is the rate determining step, which means that the reaction here involves 2 molecules because we know the rate determining step is bimolecular, and it does involve 2 molecules. Here I've already written this molecule and this molecule for you, so you might have to pause and write it in your own stuff. But I didn't want to draw it out. Okay. So this molecule on the left is the substrate. Right? And then of course this molecule on the right is our nucleophile. But I guess you already knew that because it was in the same configuration that I always write my nucleophiles. Okay, let's look at the substrate for a second here. So we have this. What the heck is that? Well, it's a halogen. We know it's a halogen. Specifically, on a substrate, we call that the leaving group. Very often, leaving groups are halogens. Halogens are good leaving groups, except for fluorine, not fluorine, okay? So iodine, bromine, chlorine, those are all decent, they're good leaving groups. But there are other leaving groups as well that aren't halogens, okay? One pretty common one that a lot of professors like is this OTOS group, okay? That's just an awesome leaving group. And if you Google what it looks like, you can see why. It's because it has a lot of resonance. Once it leaves, it has a lot of resonance. So it's resonance stabilized, which means it's stable once it leaves. And if something's stable once it leaves, then it's good at leaving because it doesn't really care. I can leave, I'm stable without you, kind of stuff. Honestly, I don't remember on the top of my head what the OTOS group looks like, but it is one of the more stable leaving groups known, okay? So it's just a really good leaving group. Okay, so we have, this is called a leaving group. We got that now, okay? So let me just, leaving group. That's how I'm going to write that. what else do I need to talk about here? Okay, so our leaving group is somewhat electron withdrawing, okay? It's pulling the electrons toward it in this bond, okay? Now what that does is, yeah, you know, it makes the bromine slightly negative, okay? But more interesting to me is it makes the carbon that it's bonded to slightly positive here. This carbon right here is slightly positive, all right? Okay. Now we know that our substrate is in a solution, right? And we've also poured some nucleophiles in there. So there's our nucleophile. Now if the nucleophile is negative, right, what is negative attracted to? Positives, exactly, right? So if we see that we have a negative here, it's attracted to positive. What's positive? Well, this carbon is positive. Now, it's only slightly positive, but it's positive enough to make a difference. It's positive enough to cause an attraction. And that's exactly what happens. So the nucleophile and one of its lone pairs comes and attacks the positive, slightly positive carbon. Now, what we have here is, what I've drawn right now is I've drawn us forming a bond to that carbon, right? These two electrons are going to form that new bond. Well, we can't have 5 bonds on carbon. So as this nucleophile is attacking, the bromine will end up leaving, okay? But let's pause real quick. Let's pause real quick, okay? So the nucleophile is very negative. But remember, this bromine, this leaving group over here, it's pretty big leaving group. It's bromine, it's a good size, but it's also slightly negative, okay? And the nucleophile is also negative. So do you think that the nucleophile wants to get close to the also negative bromine, negative-ish bromine? No, because you've got repulsion there, okay? So what happens is the nucleophile is going to attack from the back. There's also a few other reasons why this occurs, which involves orbitals, but the important thing here is to know that the nucleophile needs to attack from the opposite side that the bromine's on, okay? And I think the easiest way to remember that is just, you don't want that electron-electron repulsion. So when this nucleophile attacks, it really does have to attack from the back. That's why I drew this arrow over here. You will not see me drawing it like that, right? It doesn't want to go near the leaving group, okay? So it's going to attack from the back, and then of course that pushes the bromine off, okay? So let me write here, because this is very important. Backside attack. Okay, that is something that is specific for the SN2. Well, it's important in the SN2 reaction. Okay, so right now the leaving group is on the dash. So if the nucleophile attacks from the opposite side and forms a bond, what's the opposite of the dash? You know, the opposite of a dash is, it's a wedge, right? So a wedge is a good it's kind of on the other side. It's pointing away from the dash. So it's pretty good guesstimate for opposite, okay? So when the nucleophile attacks, it attacks from the back and it's going to end up being in the wedge position. And this methyl group kind of gets pushed that way, okay? So now what we're going to have is we're going to have our nucleophile on the wedge because it did backside attack. So it's on the opposite side now. And our bromine molecule has left the building. So it's just floating around, it's leaving, it's doing its thing. And that's pretty much, that's it. So now the important thing here is that every single time your nucleophile attacks the substrate, it attacks from the back. So 100% of the products that you form are inverted. So you get 100% inversion. Okay? What that means is every single one of your products that you formed has the inverted stereochemistry, okay, compared to where the leaving group was before, right? Anything else that I need to talk about that? Yeah, that's pretty much it. Okay, so let's look at these bullets we have. So, firstly, I made a little bit of changes here. I wanted to specify that, that nucleophiles favor accessible carbons. What does that mean? Well, it has to do with the substitution of this carbon that it's attacking, okay? So for example, methyl, if this was a methyl carbon, then it would have hydrogens on it with its leaving group, okay? Now hydrogens are not they're pretty small, okay? So it's easier to access this carbon when these groups are small because there's less crowding, right? But if you have, a tertiary carbon, right? If all of these are, R groups, they're carbon groups, then the nucleophile has to do backside attack, but it has to kind of get around these bulkier groups, especially if whatever alkyl group you have is a bulky group, right? The nucleophile is trying to navigate. There's too much steric hindrance, right, for the nucleophile to get in. So the nucleophile prefers to attack a carbon that is a methyl halide, okay? And then next after that, it would prefer a primary halide, and then next after that, it would prefer a secondary halide, and then lastly, its least favorite is tertiary. In fact, most people teach that tertiary, you don't do SN2 on tertiary, okay? It's just too crowded. The nucleophile just can't get in close enough to attack and form that bond with that carbon. Too much crowding. So you will not have SN2 on tertiary. Okay. The other thing that is important here is when you do an SN2 reaction, you have to have a strong nucleophile. Why is that? Why do I need a strong nucleophile? Oh, that just reminds me. I forgot to talk to you guys about strong and weak. Well, I'll talk to you about it very shortly now. Why do we need a strong nucleophile? First of all, what is a strong nucleophile? Like, what does that even mean? Well, the word strong, when I go through this whole section, when I say strong, that means it has a negative charge. What do you mean, Renee? What I mean is you've got nucleophiles and we have bases, okay? And the way that you know if you're working with a strong nucleophile or a strong base is if there's a negative charge somewhere on that molecule, okay? So if I were to draw, let me just give you a few. I'll give you a little quiz here. Okay, so I've drawn two molecules here. Okay, now I don't know which one's a nucleophile, and I don't know if which one's a base. I don't know what they are. That's not the question. The question is which one's strong and which one's weak. Well, this one right here has a negative charge, so automatically that tells me that this molecule is strong. Is it a strong base or is it a strong nucleophile? I don't know that yet. You don't know that yet, okay? We'll talk about that later. All you know is it's strong, okay? If you look at this molecule, does it have a negative charge? No, it doesn't have a negative charge, so it's not strong, therefore it's weak, okay? And so that's all you need to know right now, okay? So here, notice the nucleophile that I drew has a negative charge on it. That's supposed to tell you, hey, I'm a strong nucleophile, okay? This reaction requires a strong nucleophile. Why? Because let's look at our Let's look at our positive charge over here. I kind of covered it up. Let's draw it again. There we go. You see how that's partially positive? That means it's slightly positive, okay? So there's not a lot of oomph. I spit everywhere. There's not a lot of oomph in that positive, okay? It's not a strong attracting force for the negative nucleophile. So if you want this reaction to actually occur, and the positive charge is very weak, it's not, it's very small, then you need a very big negative to actually hone in on that small little positive, partial positive. Otherwise, they won't be able to see each other, okay? So the strong nucleophile is what's generating the attractive force between them, okay? If you had a small positive and a small negative, there would not be enough attraction between them for them to actually find each other realistically, quickly enough, all right? They wouldn't even see each other, basically. All right. So that's why you need a strong nucleophile, because you have a very weak, partially positive. And that's always true with SN2. So, okay, Renee, I need a strong nucleophile. I understand why I need a strong nucleophile. But what are my strong nucleophiles? The answer to that is a mnemonic to help you memorize, okay? Luckily, there's only, I think, 4. Let's see what it is. So here's the mnemonic. Mnemonic is, bro, I really suck corn nuts. Look, I'll even use a Z because I'm cool like that. Okay, Renee, bro, I really suck corn nuts. What does this mean? All right, well, bro stands for BR minus. Notice it's negative, but of course we knew that, right? Because they're strong nucleophiles, so they have to be negative, all right? All right, so BR minus, I minus, that's what the I stands for. Okay, really suck actually stands for 2 things. It stands for RS minus or HS minus, okay? So the important part is the negative sulfur atom. I don't care if I have an alkyl group or a hydrogen. I don't care if either one of those, there's fine, right? The important part is that I have that negative S because I need that strong negative charge to do the attacking. So it's the sulfur atom that's attacking because it's the sulfur atom that's negatively charged. And then corn nuts stands for CN minus. But I think it's important for us to actually draw this out. So that's cyanide anion. So that's C triple bond N. Oh, wow. And there's a lone pair on the nitrogen and there's a lone pair on the carbon. Because there's a lone pair on the carbon is negative. So the important part here is to know that, first of all, to know what it looks like, okay? Everybody draws it like this, but you need to know that there's a triple bond there and that it's the carbon that's negative. And since it's the carbon that's negative, it's the carbon that attacks and forms the bond, okay? So, bro, I really suck corn nuts. These are your strong nucleophiles. Now, if you have these are from my professor. If you have, there are more strong nucleophiles. So you do want to pay attention if you're in an organic chemistry lecture to specific nucleophiles that maybe your professor adds on to this list, okay? Because this list is not exhaustive, right? These are the main ones, though, from my experience. All right, so you need a strong nucleophile, and the strength of the nucleophile plays a direct role in the rate of an SN2 reaction. Now, we're going to talk more about the rate of SN2 and SN1 kind of later on. So we'll come back and talk more about rate later. All right, so important things to remember. 1, If you want to do SN2, you can have a methyl halide, primary halide, or a secondary halide. It won't occur with a tertiary halide. Next is you need a strong nucleophile. Oh, specifically it occurs fastest with a methyl, and then next fastest with a primary, and then the next fastest, or pretty slow with a secondary. It's okay. And it occurs so slowly on tertiary, it basically doesn't happen. Okay, we just say it doesn't happen. All right, the other thing is your product, every single one of your product molecules has a nucleophile instead of your leaving group, and that nucleophile is on an inverse position compared to where your leaving group started. Okay, so here we had this on the dash, which means inversion of that puts our nucleophile on a wedge. Okie dokie. I think that's it. All right, yeah, that's pretty much it. So let us move to SN1 reactions. Well, this video is 20 minutes, so let's cut it off for now and we'll have a new video for SN1 reactions.